Imagine a universe where time is not absolute, where the ticking of a clock can vary depending on your speed and position in the cosmos. Picture a reality where the faster you move, the slower time passes for you. This isn't science fiction, it's a fundamental aspect of our universe. In this universe, time stretches and shrinks depending on how fast you move. Just like a rubber band that can be pulled and released, time itself is flexible, bending to the will of speed and gravity. This is the universe according to Albert Einstein's theory of relativity. Einstein's groundbreaking work in the early 20th century changed our understanding of the cosmos forever. His equations revealed that time and space are not separate entities but are interconnected in a four-dimensional continuum. It tells us that space and time are intertwined, forming a fabric called spacetime. This fabric can be stretched, compressed, and warped by the presence of mass and energy, much like a sheet of fabric can be distorted by placing objects on it. Einstein's theories revolutionized our understanding of gravity. Before Einstein, gravity was thought to be a mysterious force acting at a distance as described by Isaac Newton. But Einstein showed us a new way to look at gravity. They showed that gravity is not a force acting at a distance but a curvature in this fabric of space-time. Imagine placing a heavy ball on a trampoline. The ball creates a dip, and smaller objects roll towards it. This is a simple analogy for how gravity works in Einstein's universe. Massive objects bend space-time around them, much like a bowling ball placed on a trampoline would create a dip. The more massive the object, the greater the curvature it creates, and the stronger the gravitational pull we experience. This curvature of space-time is what we experience as gravity. It's a beautiful and elegant explanation that unifies our understanding of the universe, from the smallest particles to the largest galaxies. The Earth orbits the Sun not because they are pulling on each other with invisible strings, but because the Sun's mass warps space-time, creating a path that the Earth follows. This warping of space-time guides the planets in their orbits and shapes the very structure of our universe. One of the most profound consequences of Einstein's theory of relativity is the existence of a universal speed limit, the speed of light. This concept has revolutionized our understanding of the universe and the laws that govern it. Light travels at an astonishing 299,792,458 meters per second, a speed we denote with the letter c. This speed is not just a large number, it is a fundamental constant of nature that plays a crucial role in the fabric of space and time. According to Einstein, nothing in the universe can travel faster than light. This limitation is not due to technological constraints, but is embedded in the very structure of our universe. The speed of light acts as a cosmic speed limit, ensuring that the laws of physics remain consistent and predictable. This is not just a technological limitation, it is a fundamental law of nature. The speed of light influences everything from the behavior of particles at the smallest scales, to the dynamics of galaxies, and the expansion of the universe itself. As an object approaches the speed of light, its mass increases infinitely, and it would require an infinite amount of energy to accelerate it further. This phenomenon, known as relativistic mass increase, is a direct consequence of Einstein's equations and has been confirmed by numerous experiments. The speed of light is not just the speed of light, it is the speed of causality, the speed at which information travels in our universe. This means that any cause and effect relationship is bound by this speed limit, ensuring that information cannot travel faster than light. It governs the way we perceive events and the order in which they unfold. The finite speed of light means that we are always looking into the past when we observe distant objects in the universe. This delay in information travel shapes our understanding of cosmic events and the history of the universe. The implications of light's constant speed extend beyond physics into our daily lives. Technologies like GPS, telecommunications, and even the internet rely on the principles of relativity and the finite speed of light to function accurately. Understanding this universal speed limit helps us navigate and make sense of the world around us. As we continue to explore the universe and push the boundaries of our knowledge, the speed of light remains a guiding principle, reminding us of the intricate and beautiful laws that govern our reality. It is a constant race not just of light but of our quest to understand the cosmos. Could there be ways to bypass the speed limit of light? This question has fascinated scientists and dreamers alike for generations. The speed of light, approximately 299,792 kilometers per second, is the ultimate speed limit in our universe, according to Einstein's theory of relativity. But what if there were ways to cheat this cosmic speed limit? One intriguing possibility comes from the theoretical concept of wormholes. These mysterious structures are often depicted in science fiction as gateways to distant parts of the universe, allowing for instantaneous travel across vast distances. Wormholes are hypothetical tunnels that connect two distant points in space-time. They are solutions to the equations of general relativity proposed by Einstein and physicist Nathan Rosen, hence sometimes called Einstein-Rosen bridges. Imagine folding a piece of paper in half and poking a hole through it. This simple analogy helps us visualize how a wormhole might work. The paper represents the fabric of space-time and the hole is the wormhole, creating a shortcut between 2 points. The hole represents a shortcut, a shorter path between 2 points on the paper that are otherwise far apart. In theory, a wormhole could connect two distant regions of space, making it possible to travel from one to the other in a fraction of the time it would take to travel through normal space. Similarly, a wormhole could potentially allow us to travel vast cosmic distances in a shorter amount of time. Imagine being able to journey to another galaxy in a matter of seconds, rather than millions of years. This concept, while tantalizing, remains firmly in the realm of theoretical physics. However, wormholes remain highly speculative. Despite their popularity in science fiction, we have yet to find any empirical evidence that they exist. The mathematics behind them is complex and suggests that even if they do exist, they might be incredibly unstable. Their existence has not been proven, and even if they do exist, keeping them stable and traversable would require exotic forms of matter with negative energy density, something we have never observed. This exotic matter would need to have properties that are vastly different from anything we know, making the practical use of wormholes a significant challenge. Another mind-boggling concept is the warp drive, a theoretical propulsion system that could potentially allow faster-than-light travel by manipulating space-time itself. Instead of traveling through space, a warp drive would distort space-time around a spacecraft, creating a bubble of warped space. Imagine a surfer riding a wave. The surfer moves forward not because they are paddling, but because the wave is carrying them. Similarly, a warp drive would propel a spacecraft by creating a wave in space-time, compressing space in front of it and expanding space behind it. While mathematically conceivable, the engineering challenges of creating a warp drive are astronomical. It would require unimaginable amounts of energy and manipulation of gravity on a scale we can barely comprehend. While Einstein's theories suggest that nothing can travel faster than light, there is a hypothetical exception: tachyons. Tachyons are hypothetical particles that always travel faster than light. Unlike ordinary particles, which gain mass as they approach the speed of light, tachyons would lose mass as they slow down towards the speed of light. The existence of tachyons has never been proven. If they do exist, they would challenge our understanding of causality, as they would allow for communication that violates the order of events. One of the biggest obstacles to faster-than-light travel is the sheer amount of energy it would require. According to Einstein's famous equation, E equals mc squared, mass and energy are equivalent. As an object approaches the speed of light, its mass increases infinitely, meaning it would require an infinite amount of energy to accelerate it to the speed of light. Even if we could somehow circumvent the infinite energy barrier, the energy requirements for near-light-speed travel are still astronomical. To accelerate a spacecraft to a significant fraction of the speed of light would require more energy than we currently produce on Earth in an entire year. Faster-than-light travel could potentially lead to violations of causality, the fundamental principle that cause must precede effect. If we could travel faster than light, we could potentially send messages back in time, creating paradoxes that defy logic. Imagine traveling back in time and accidentally preventing your parents from meeting. If your parents never met, you would never have been born. But if you were never born, how could you have traveled back in time in the first place? Such paradoxes suggest that faster-than-light travel, if possible, might be governed by rules we are yet to comprehend fully. The current scientific consensus is that faster-than-light travel remains highly improbable. While intriguing possibilities like wormholes and warp drives exist in the realm of theoretical physics, they face formidable theoretical and technological challenges. However, the lack of definitive answers also fuels our curiosity, and drives us to explore the universe's mysteries further. As our understanding of physics advances, we may uncover new laws and phenomena that could revolutionize our understanding of space, time, and the possibilities of faster-than-light travel. The human spirit yearns to explore, to push the boundaries of what we know and venture into the unknown. The possibility of faster-than-light travel, however remote, ignites our imaginations and inspires us to dream of reaching distant stars and galaxies. While we may not have the answers today, the quest to unravel the mysteries of the universe continues. Every new discovery, every step forward in our understanding, brings us closer to comprehending the true nature of space, time, and the possibilities that lie beyond our current reach. The universe is vast and full of wonders, and who knows what incredible discoveries await us as we continue to explore the cosmos.